So A ground means analog ground and D ground means digital ground. So we basically have two different grounds. One is analog ground, another is digital ground. The analog ground is actually the ground for the input signal or analog signal, which is V in, and digital ground is the ground for VCC, which, as we know, is connected to the 5 volt plus 5 volt power supply to power up your chip, and sometimes it also acts as a reference voltage. So these are two different things. Okay, V in is your analog signal and VCC is either your reference voltage, or you can say it is just used to power up the chip. So these two grounds are different. So the question is why, why do we need two different grounds? We could have simply connect both the grounds at the same ground terminal. The thing is, whenever we convert an analog signal to digital signal, we often get transient voltages. Okay, transient voltages are voltages which remain active for a very short period of time. They are basically like voltage spikes. Okay, so whenever we convert that, if our grounds are not separate, then these transient voltages or digital transients can affect your input analog signal. All right, so to ensure that this type of digital transients do not affect our input signal, analog input signal, we have two separate grounds. This is one of the way of understanding this, and this is the most appropriate way. There is another way. If for some reason some of you might have difficulty in understanding whatever I just said, there is another analogy which is also acceptable actually, and in that way you can say that what are actually grounds. We always connect the negative terminal to the ground. Whenever we give any type of connection, we connect the negative terminal to the ground. So the negative terminal actually acts as the reference for your positive terminal. Like, say if you're connecting 10 volts to your positive terminal and your negative terminal is grounded, then you say that my input is 10 volt. But if you connect your positive terminal to 10 volt and connect your negative terminal to 5 volt, in that case your input voltage is actually 5. So the negative terminal basically provides us the reference voltage. So you see that if in both the cases, like in analog and digital, we have the same reference point, then if there is a transient voltage while you have converted your analog to digital, then definitely that transient voltage will also affect your analog signal, because both the reference voltage are exactly the same. So that's why often there are two grounds. Anyway, the first explanation is more appropriate. Okay. Now, if you see the connections in this book or in some other experiments, software-based experiments, if you see the connection, you will often see that both of these grounds are connected to the same ground. Okay, although we are saying that they should be grounded in two different grounds, but most of the time they are grounded in the same ground, because whenever you simulate or work on simulation, work on software, we automatically assume this is an ideal environment. So we don't have to worry about these transients and all these things. But in any practical scenario, if you ever see the connection of ADC 0804 in real life, you will see that the two grounds are different. Okay, so whenever you go for practical implementation, you must keep in mind that these two grounds should have two separate grounds. But while simulation and while doing simulation with software, you can actually leave them be the same ground, no problem with that. So now let us try to summarize whatever we have learned so far about this ADC 0804.
Sir, could you give some more time on the previous slide to write?
Oh yeah, sure.
Thank you, sir.
Finished?
Yes, sir. Finish, sir.
All right, so let's see how much you have understood so far. So on the left hand side of the screen, we summarize the pin description that we have learned so far from yesterday's class. So first of all, we make CS equal to 0 and then send a low to high pulse to WR, and thus we start the conversion. Then we know that we have to keep polling INTR. We already know what is polling, so nothing to discuss over there. We'll keep polling INTR until it goes low. When INTR is low, then we have to make sure that CS again becomes 0, and we will send a high to low pulse to RD pin so that we can read the data. So based on this information, let me see if you can tell me which are what wave shape over here. I mean the first one, it is the wave shape of which pin?
CS.
CS, okay, right. This is CS. What is the next one?
WR.
Right, WR. Okay, forget about the third one. What is the fourth one?
Inter.
Good. And very obvious, the last one is our RD pin. And this is actually your data pin, okay, D0 to D7. So you see that at the final step, our CS is 0. we make a high to low pulse in RD, and thus from that point onwards, we send out our data. So our data is sent out using the D0 to D7 pin. So this is the summary of your ADC 0804. Whenever you want to go for coding, this figure is mandatory to have in your mind. This is your not table, sorry, this is your figure 13.2 of your book. So you must have this figure, otherwise it will be very difficult for you to code. Okay? Having this entire scenario in mind is a bit difficult. So you need to have this figure drawn so that you can appropriately code, complete your code. Anyway, so up to this, if any one of you have any question or any confusion, please ask.
Sir, in the book, this figure we have WR and Inter and RG. They have bar at the top. Is it indicating? Right. Is it indicating the complement or what, sir?
It depends on your figure 13.1. Can you go back to figure 13.1? If you have your book open, go back to 13.1.
Yes, sir.
Look at this pin, CS, RD, WR, and INTR. Just at the starting of these pins, can you see a small circle?
Yes, sir.
So those circle means the inverse, right?
Inverse, yes, yes,
so
sir.
Based on that connection, they gave that bar over here. Since I did not draw the circle, I just gave you the normal idea. But based on your connection, you need to specify whether there will be bar or not. Understood
yes,
now? Clear?
Yes, sir. Yes, sir.
Good question. Good observation. Okay. Anyone else? Any other question?
Why do we need the TF pin? Because there is no other chip in the IC.
Which one? Why do we need which pin?
TS pin. The chip select pin.
Oh, chip select pin. Why we need the chip select pin?
Yes, sir.
That pin is responsible for powering up this ADC 0804. If that pin is not low, your chip will not work.
We can always make it low for.
Oh, so your question is why did we make CS high? That should have been the right question. Was that your question?
Kind of, sir.
Okay. No, yes, the questions are two different. If you ask, sir, why do we need CS pin, then the answer is very simple. You need CS pin to become low to activate the chip. So that is one answer. And if your question is why CS goes up, then that is a completely different scenario. So what is your question?
My question was, sir, there is no other chip to select. So why do we need this pin in the chip?
There is wait, you are saying there is no other chip to select. Your CS is responsible for only this chip. Why will it be related to some other chip? That is something I'm not getting from your question.
মানে স্যার CS পিনটা যদি না থাকতো তাহলে তো কোনো সমস্যা হইতো না। আমার কোশ্চেন হচ্ছে এটা, CS পিন যদি অলওয়েজ এমনিতেই লো থাকতো।
CS পিন যদি CS পিন না থেকে CS পিন সবসময় লো, এটা হচ্ছে কোশ্চেন। Oh, okay. Now I get your question. The question is, what if we don't provide the control of CS pin to the programmer? Rather, we make sure that the CS pin is always low, so that the chip is always active, right?
Yes, sir.
Okay. Now, what will happen is, we talked about transients. Do you remember voltage transients? We try to avoid those things, but still, whenever we are doing this type of conversions, very often we might face voltage spikes, okay? Unexpected voltage spikes. Okay, so what happens is, say your CS is entirely low, okay, it is always low, and suddenly in that stage your voltage spike affects the WR. Suddenly in WR your voltage increases. So that will act as a low to high pulse in WR, right? So what will your chip see? The chip will see that my CS is low and I received a low to high pulse. That means I need to start the conversion. So it doesn't matter whether your previous conversion has finished or not, your WR will start a new conversion. So you get the problem, right? The same thing can be applied for INTR as well. Say suddenly there is a voltage drop. So what will your INTR face? Okay, in this case, INTR is not dependent on CS, so forget about that. but the RD will be equally affected. Did you get the point? What I'm trying to say?
জি স্যার, তাহলে স্যার হচ্ছে রাইট পিনটা তো সবসময় হাই থাকতেছে যতক্ষণ আমার ইয়ে থাকতেছে মানে,
Right. Yes. Yes. It is normally kept high.
তো এই প্রবলেমটা তো তাহলে হওয়ার কথা কথা না, যখন হচ্ছে রাইট পিন হাই থাকবে তখন তো অলরেডি হাই আছে।
Okay. So before you start the next conversion, you need to make sure your right pin goes low, right?
Yes, sir.
What if you get a spike at that point before you have intended? When your WR is low, see, your WR is low in these places as well. So what if you get a spike in those places? What will happen? You want to start the conversion from this point, right? So if you get a spike over here, then you will start the conversion from here. That is something we don't want, isn't it?
জি স্যার।
So this is where this is actually safety reason, okay, why CS is made low. Another thing is that see, whenever we turn on a TV or air conditioner, we press a button, right?
Yes, sir.
Do you keep the button pressed throughout the time your TV is on or your AC is on?
No, no,
After
sir.
a specific time, you leave it, right? After a few fraction of a second or a second, you leave that button.
Yes, sir.
So even though this one is used to activate the chip, we don't keep it low throughout the entire period. We make sure again it goes to its normal state. Have you got your answer?
Yes, sir.
Sir, could it be also to allow us to use multiple chips so we can measure multiple voltages using the same digital pins?
Using the
Same digital pins, we can use multiple chips so we can select a particular chip to measure.
Oh, so you're talking about different ADCs.
Yes, we can
Yeah,
use
it might
different
happen.
ADCs to measure.
Yeah, it might happen that with one MUSI you are connecting different ADCs. So that way you can also control which ADC you want to use. That can also be done. All right. So, okay. Let us see another ADC. Okay. Still, we are not going into coding. Let us see another ADC first. So the previous one was ADC 0804 and now this is ADC 0848. All right then. So this has also a resolution of 8 bits, which is same as before. This is the main difference. Okay, this is an 8-channel ADC, meaning that now you have got 8 input channels. Okay, it is better to see the figure. It is there in your book. I will not draw. Figure 13.8. The figure of ADC 0848 is given. So what will happen is now you have got 8 different input channels. That means you can connect 8 different sensors or transducers to your ADC. All right, but of course any one channel will work at a particular time. I mean, it is not like that the 8 channels you can take input simultaneously and convert them simultaneously. That's not the case. You can convert any one channel at a specific time, but you can connect up to 8 devices to this particular ADC. Is it okay? So those who have opened the book, you will see that most of the pins are actually similar. So we will not waste time explaining those pins. We will just discuss the pins which are different. Okay, let me just write the pins which are exactly the same. All right, so all these pins are there in your this new ADC 0848, and this description of these pins are exactly same as before. So now let us look at the new pins that we have.
Sir,
Hmm?
can you just go back to the last slide a bit? I missed one point. Thank you. Yes, you may proceed.
Okay, so the pins that are a bit different from your previous ADC are DB0 to DB7. These pins, your DB0 to DB7, they can be used either as input ports or input pins or as output pins. Previously, in the previous chip, this was analogous to D0 to D7, which were your data output pins only. But now, in this case, this DB0 to DB7, they can be used either as input or as output. Okay, just give me a second. Sorry for the disturbance. So as I was saying, this can be used both as input and output. We already know why output, because whenever we have done the conversion, we need to send the data out. So that is when these pins act as output. And why do they need to act as input? Because now instead of one channel, we have got 8 channels. So we need to specify from which particular channel we will take the input. So in order to specify the channels, we also need these pins, and in that case, they will act as input. We will discuss more about this channel address a bit later. For the timing, this much is enough. So let us look at the conversion process. Our D out is given by V in divided by step size, where D out is our digital data output and V in is our analog input voltage. We already know what is step size, so I have not written anything about the step size. Okay, I hope you have understood this thing. So now let us try to solve some maths and let's see how much you have understood. Okay. All right, so the question is, we are given the reference voltage, which is 2.56 volt. We need to calculate D out if V in is 1.7 volt and 2.1 volt. Okay, should be very easy. So let's start with the first one. We know that our D out is equal to V in divided by step size. Having known this, what is my V in for the first case? Can anyone say? Come on, what is my V in?
1.7 volt.
7 volt.
Yeah, 1.7 volt, very obvious. And what is the step size now?
0.01.
0.01. Okay, let us do the rough calculation over here. Okay, how did you come up with 0.01? Just tell me the calculation.
2.56 divided by 2 to the power 8.
2.56 divided by 2 to the power 8. Okay, so if that is the case, how much do we get?
0.01.
Okay, 0.01, or instead of writing 0.01, I think we can write 10 millivolt as well, isn't it?
Yes, sir.
The calculation is correct. Did all of you understand the calculation? How we found out the step size? All right, so if you say nothing, I will assume you have understood. So divided by 10 millivolt, the answer you end up getting, sorry. How much is the step size? Did you say? Yeah, 10 millivolt. Yeah, sorry, yeah, right. So 10 millivolt. The answer we end up getting is 170 in decimal. So if you convert that decimal number into binary, we get 10101011. So what is the important thing to see over here is this one will be sent out from D7 and this one will be sent out from D0. So these are the output that we sent out using DV0 to DV7. So applying similar logic, if we find the answer of the next one, where the only change is your V input, now the V input is 2.1, the answer we get is 201 in decimal. Convert that to binary, we will get 11010010. All right, so this one will be sent out using D7 and this one will be sent out using D0. So if there is any confusion, please ask now. Even if you think your question is very silly, still you should ask and clarify from here. So if there is any confusion, please ask. Time and again, I'm saying the same thing. All right, so I'm assuming there are no questions, so you understood everything. Let's move forward. Okay, so the next pins are MA0 to MA4. I have told you to see the figure. So if you have opened the figure, you can correlate. Otherwise, just hear me out and correlate later on. The DB0 to DB7, we have got 8 pins over here. Among these 8 pins, the first 5 pins, that is DB0 to DB4, they are also known as MA0 to MA4. That means the first 5 pins of DB0 to DB7 are also known as MA0 to MA4. So these are actually the 5 pins which are used to specify the channel's address. All right. And when we select output, then all the 8 pins are used. But when we make these pins as input, that is when we are reading the channel's address from the MUSI, then we say that these are my input pins. Again, as I said, we will see in details how we can select the channels just after this page. Okay, so that is your MA0 to MA4, also known as multiplex address. Finally, we have got the WR. So again, as usual, when CS is equal to 0 and we provide a low to high transition, then your ADC 0848 will make sure that it is reading the data, or it is reading the channel address from the multiplexed address pins. Okay, so whenever we make a low to high transition, automatically your ADC will read the address of the channel and it will take input from that particular channel only and will start the conversion. Then automatically your ADC will make sure that these pins will now act as output. It will not work as input anymore. Once it has read the channel address, it will make sure that these pins will be ready for sending the output. You don't have to do anything. Then the conversion time is set by an internal clock. However, it is always faster than 40 microseconds. This is the specification of your ADC 0848. Now let us see the channels.
Sir, it is higher than 40 microsecond.
Lower. It is
Lower
the maximum time is 40 microsecond. So it will always be less than 40 microsecond.
Yes, sir.
Okay, then. So now finally we come to the channels. As we have already discussed that there are 8 channels for the analog inputs, but they cannot be used all at the same time, and we need to select which channel to use. We have already also discussed that MA4 to MA0, they signify which channel to use. All right then. If we want channel 1 to be selected, can you tell me what should be the hex number that should be given as the channel input? Tell me the hex number that should be given as input to select channel 1.
088.
Yeah, right. So 08H, the next one will be 09H. Then it becomes very easy. 0AH, then 0BH, and so on. Okay, we can just find it. So anyway, so these are the values that you should actually know, because says at some instance you need to select channel 4. So now you can control from your MUSI which channel you want to take input from, because all these are connected to your MUSI 8051, right? So you want to take input from channel 4. So you need to send 0BH to the MA0 to MA4 to MA0 pins. When we'll go to coding, it will be much more easier to understand. But for the timing, just know that these are the values you need to specify in order to select a specific channel. Having said so, let us now try to summarize whatever we have learned or whatever we have gone through so far. All right, so please try to understand this portion now finally. So the summary that we get is while CS is equal to 0 and RD is equal to 1, we need to provide the address of the selected channel by these pins. Then we have to apply a low to high pulse to the WR pin to latch in the address and start the conversion. After that, we need to keep polling INTR, and when INTR goes low, we need to make sure that CS is again equal to 0 and apply a low pulse to RD to get the data. So let us correlate with the wave shapes that we have now. So while CS is equal to 0 and RD is 1, then we have to provide the address to the selected channel. That means in this case now, we will provide the channel address. So which pins will come over here? The pins that will be involved are MA0 to MA4. So these are the pins that will be involved because we need to send the address first. After that, we need to apply a low to high pulse to the WR pin that we have done. Then we will get this address and we'll start the conversion. Later on, we'll keep polling the INTR. Whenever INTR goes low, we know that the conversion is finished, and after that we need to apply another low pulse to RD. So we apply another low pulse to RD over here. As you can see, after your INTR has gone low, we apply a low pulse to RD, and we know that the data is now ready to be read. So over here that we get, what we get is data, and the pins involved are DB0 to DB7. So this is the wave shape that we get from the summary of whatever we have learned so far. Again, this is there in your book. This is figure 1310. So if you want, you can see from the book as well. Anyway, before I let you ask questions, remember that after this we'll see a code. In order to code, this is a figure that you always need to have. Without this figure, it becomes very difficult for you to code. Once you have this figure, then you know which pin to make high, which pin to make low, which pulse to send, what to do. I mean, everything is quite clear from this diagram. But if you don't have this diagram, then it becomes a bit difficult to keep track. Not impossible. A lot of people does it without the wave shape as well. But as starters for us, it becomes a bit difficult. Okay. All right now. So if any one of you have any question, you can ask now. কারো কোনো কোশ্চেন নাই? Yeah, if there is no question,
স্যার সিঙ্গেল এন্ডেড মোডের যে টেবিলটা বলছিলেন স্যার, সিঙ্গেল এন্ডেড মোড বলতে এখানে কি বোঝানো হচ্ছে স্যার?
single ended mode, that means you can use only any one specific channel at a particular instant of time. You cannot use two or more channels or all the channels at the same time. At a specific time, you can use any one channel. That is what is known as, sorry for all this noise. Okay. All right. Yeah. So you can use any one channel at a specific time. So that is what is known as single-ended mode. Is it okay?
Okay, sir. Then it will be either MA4 or MA3 or MA2.
No. It will be then either channel 1 or channel 2 or channel 3 like this.
Oh, the CS1, CS2.
Yeah. These are 8 input channels. You are taking inputs from these 8 channels. So you can use any one channel at a specific period of time. Say in channel 1, you have connected a temperature sensor. Okay. Say in channel 2, you have connected a humidity sensor. In channel 3, say you have connected what other sensors are there. Some other sensor. Okay. So you can select which channel you want to convert the data. Say first of all, you are reading data from channel 1. Then you finish the conversion. After that, you go to channel 2. So how do you select these channels? These channels are selected based on the values in MA4 to MA0. Is it okay now?
Okay, sir.
Right.
Yes, sir.
Any other question, anyone? Yeah. So if there are no other questions, let me stop sharing. All right.